Hello everyone, welcome to another example set from Physics 30, Nuclear Theory, that's Unit 6, and this is the last lesson in Unit 6. This is Lesson 7, Particle Classification. So, here we've got a proton and an antiproton colliding. In class we would have talked about electrons and positrons colliding. That's a much more common situation that can be studied, but in theory proton antiproton collisions can happen too. We would get two gamma photons being produced because of the conservation of energy and the conservation of momentum, and so our job is to determine the frequency of the gamma photons. And conveniently enough, we're ignoring that initial kinetic energy. So let's go ahead and just sketch out what this really means. Just going to represent my proton as being here and my antiproton as being here. And let's just say they touch. It's not so much a collision, just a touch, because the kinetic energy is 0. So if that happens, they're going to annihilate, because matter and antimatter always will do that, which means they're turned into pure energy in the form of gamma photons. And gamma photons, of course, have the speed of light, so we could say arbitrarily in any direction there would be a gamma released. And because of conservation of momentum, then there must be another gamma released in the exact opposite direction. Otherwise, we break conservation of momentum. So that's a gamma, that's a gamma. The question is, what's the frequency? Well, we're going to talk about energies. So we're going to talk about the sum of energy initial being the same as the sum of the energy final. And of course, this is convenient because we don't have any kinetic. So the only energy in this proton and in this antiproton is coming from its mass. So I'm going to make a statement here. I'm going to say the energy of the proton plus the energy of the antiproton is going to be equal to gamma, actually I should say, of course, the energy of the gamma plus the energy of the other gamma. Okay, what are we going to use to get our energies? Well, we can use the Einstein's mc squared to get the energies of the protons and the antiprotons, because of course they have a mass, and then they'll turn into gamma photons which do not have a mass. And for the energy of a photon, we know that we can talk about HF. Okay, so we've got mc squared and mc squared and HF and HF. But just to simplify it a little bit, of course, because when we're dealing with the mass of matter and antimatter, the mass values are exactly the same. So I'm just going to go ahead and say that there's 2 times the mass of a proton, or an antiproton, doesn't matter, c squared, is equal to 2 times the HF, and that's going to be the frequency of the gamma. Okay, so the 2's cancel out. And so really what we're saying is that the mass of the proton times c squared is equal to HF, frequency of the gamma. And if we want to know the frequency of the gamma, we're just going to go mass of the proton times c squared divided by Planck's constant, and that's going to be the 6.63 times 10 to the negative 34 joule second version, because we're dealing with mass and the speed in meters per second, so that's a derived version of joules. So let's go ahead and do that calculation. If we do that, plug it into your calculator, mass of the proton is 1.67 times 10 to the negative 27 kilograms. Speed of light is 3.0 times 10 to the 8 meters per second. Of course, that's squared. And that's divided by 6.63 times 10 to the negative 34 joule seconds. And so that's going to give me my frequency, which is, so the frequency is 2.27 times 10 to the 23 and that of course is Hertz. There we have it. Okay, so for the last example question of Physics 30, we have a nice simple charge of an exotic particle, in this case a pi meson, which is commonly called a pion. Now, a little bit of a clue here. There's lots of different pions, pi mesons you can have. The clue here is in the name, so the annotation is pi negative. So I'm already suspecting it's a negative charge, but let's just go ahead and prove it. Because you're going to have to get used to doing this for lots of different types of weird, fancy, exotic particles. And as long as you know what they're made of, in other words, they're made of up quarks, down quarks, anti-up quarks, or we would say anti-up, anti-quark, and then an anti-down, antiquark. If they're made of these things, then we can determine what the actual charge is, because as you know, a regular up quark is a plus 2/3, a down quark is a negative 1/3, which means an anti-up is negative 2/3, and an anti-down is a positive 1/3. So in this case, we have an anti-up. So the anti-up is negative 2/3 of an elementary charge, plus the down, which is a negative 1/3 of the elementary charge. So this is going to be, sorry, just rewrite this, pi meson. Okay, so the pi meson, or the pion, is negative 3 over 3 elementary charges. Oops, should have put that inside. Elementary charge, which of course is negative 1 elementary charge. That's it. That's all for us. I'll see you next time.